Hi, I'm Yusuf.
Hi, I'm John. And this week on Geek Moniker, we're going to talk about a few of our projects this week. Yusuf, what have you been working on this week?
So this week's been great, John. It's been an ideal project week for me. It started out with an itch to learn Fusion 360, which is the CAD/CAM, industrial strength software. And after I had learned it a bunch, I wanted to actually apply it on a real project. I don't really like contrived, exercises to learn something. And lucky enough for me, you actually had a part you wanted to, model up and replicate. Do you have that part with you?
Sure. Do you want me to give a little background about what I was trying to do with it?
Sure, go ahead. Yeah.
Yeah, so here's the basic idea. So this part right here is part of a high precision polishing machine. Now, I need to make some custom tooling for this, such as to calibrate the machine. We could talk a little bit more about it later, but basically what I need to do is something that I can mount this gauge to. So my question to you was, if you were interested to help making some sort of part so I could kind of get a spare to adapt this to this. And what did you do once I gave you some measurements then of this guy here?
So I took those measurements. I drew it up in Fusion 360 and I created a model. And I can actually try to show you the model right now if I share my screen. Hopefully this is going to work. If not, we'll put a link in the description and you can have a look at the model live online. So do you have a view of this right now?
I am. I'm checking to see the stream. Unfortunately, there's a delay. Perfect. I can see you. Your screen is live on YouTube, so I think we're good.
Perfect. So this is the 3D model that I got built after putting in the measurements and designing the item. The one nice thing about Fusion 360, because it is such a full-featured industrial strength kind of application, is I was also able to generate drawings out of this. And this is quick drag and drop. Like you don't have to really do much work. It comes straight from the model. Can you see the drawing itself?
Yes, I can. Let's see. It looks like you've got a 3D model to the right, and then you've got a few different views. Now, I think a lot of times it's very standard to have an isometric view. Was there a reason why you either included or omitted that?
So these were, I think, it's descriptive of the part. It shows, kind of like the major dimensions and kind of the intricacies of it. The view in the corner, do you see this one right here?
Oh, sure. Yeah, I guess. Yes, I guess that stands in for that. Yeah, that makes sense.
Yes. Because you can't actually put dimensions on that view for some reason. So, the dimensions are just on the top side front views.
Sure. Okay, that's nice. And what about tolerances? Is there kind of a standard, the way that those get displayed here? I'm trying to look. Scale 2:1.
So I think so. I think the convention is the number of decimal places you show in the drawing is what machinists use as the tolerances that you're implying. Over here in this drawing, it's not consistent. So like some you see here is, 3 decimal places, some are 2 decimal places. Ideally, sure. I think I would, zero pad those to actually have 3 decimal places in there.
Okay, gotcha. Now, once you had these drawings, you actually went out and started looking for quotes, right?
I did, but before that, actually, one thing you went and did was get a 3D print of the part just for fit purposes. Do you have one right there?
Yes, I do. That's right. Yeah. So here is the original part right here. And here is basically our fit test part. And I was able to put this on the machine and verify that this does in fact fit on the machine, and it seems to work pretty well.
Yeah, and I think you got that printed for like $40 in 24 hours, right?
Yeah, and this could be a whole tangent. I don't know if we want to go on this. A lot of people are surprised I don't own a 3D printer. Kind of my philosophy on that is I always try to outsource something if possible. So I got this 3D printed at the UPS store in downtown Mountain View. So if you don't own a 3D printer, you want something 3D printed, maybe check, see if your local UPS store has a service like this.
Okay. So that actually segues into CNCing the part out of a metal, right? And I thought this is going to be like super expensive because, I mean, it's CNCing something from metal, even though this part is fairly simple geometry. I thought it'd be a lot more expensive than it turned out. I threw it out onto a couple of online sites. Within 15 seconds, I uploaded the part and they had quotes for me. Like, if you go with the cheap, made in China, delivered in 3 weeks option, this part's about $50, which is pretty crazy considering that, the 3D print itself cost you about 40.
Now, did you cost compare different materials when you were doing that? You talk about 3D
I
print,
did.
for example.
Yes. So basically, I ran a couple of quotes for CNCing some steel parts and some aluminum parts. They were almost similar. I did also try quoting up 3D printing in metal, and that actually turned out to be a lot more expensive.
Do you remember how much that was?
I think that ended up being about $270 a part, as opposed to maybe $90 if you get the 2-day delivery made in US option.
And what was metal? Was that stainless, or do you know exactly what that was?
I don't actually. I don't, unfortunately. I didn't dig too deeply because those prices were like quite high.
Sure.
And the one thing was that this part has fairly simple geometry, but it does have that little slot in it, which I thought would be kind of problematic to machine, but I guess not.
So I think the way that that's done is they have standard. Gosh, I actually could run and get one. I think I have one. Give me just a second. I'll be right back.
Sure.
Play elevator music.
Dum 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 dee dee dum dee dum 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 dee dee dum dee dee dum. And if anyone has questions, please do comment send a comment in, and we will be paying attention. There he comes. John's on his way back.
All right, I'm back. You hear me?
Yes, hear you.
Okay. So yeah, they use a tool that looks like this. And so it's kind of a specialty tool. So presumably they have one in stock, because I think that's a fairly standard. I think it was 3/8 width or something like that.
Yeah, it was 0.375 inch, I think.
Yeah, and so maybe if it was a special one, they would have required something special. But with this, I think this just kind of spins, makes that slot. And so even with that undercut there, I think it's pretty easy to do if you have this tool. So I think that's why it's not so bad as it could have been.
I think we got lucky there, because I do have something I learned actually, and this I think is, if people are thinking about fabricating their parts, this is interesting. So I left all the edges sharp, but normally what you do is you put a little chamfer around the edges to make them like, little bevels so that they're not super sharp. Like, yes, like on the original part.
Yeah, I don't know if you can see it though.
And I did actually run a quote with the chamfer, and that added about 20 to 25% to the price of the product, which, in this case, the chamfer isn't a critical piece of geometry. We didn't need it, So I think trying to get a cheaper part, it definitely, helps to keep things like that out, even though the chamfer was just around the, circular borders.
Sure.
So that's something like, to keep in mind if I guess you're, designing parts for cost.
Yeah, and depending on your margins, that could be huge. That could cost you quite a lot.
Yes. For the American part, which was about $90-ish, I think with the chamfers around the border, it was about 110, 115. So, not negligible. And I didn't even add chamfers to the internal slot or anything, which I assume would be a little more expensive because getting the tools in there might be more problematic. So definitely, very minor thing like I would not have considered, but turned out to be quite a significant price bump.
And maybe we should also dwell about why you do that. Why would you add these chamfers to the parts?
So I'm not certain technically, but I would think one thing would be just taking out the sharp edges, so you handle the part, it's a little easier. It might also help if, if you're fitting the part into another, mating piece, it makes it easier to slide in and out, you're not hitting sharp parts. So I would think those would be the main points. But I guess, I like the one thing that I really want to do is actually have somebody who knows machining to look at the design of this and kind of give feedback on, tips and tricks to consider like this when designing a part.
Oh, that sounds good. Now, I think one other thing that we also spent a while talking about was material choice. Maybe I can give a little background about why you might choose one material versus another for this.
Yeah, go ahead. Yeah.
Sure. So this original part here is stainless steel. And to give you some background, there's several different ways that this is a sample holder, might get used. And the basic idea, you use this to do very precision polishing. And the two dominant ways to do that are to use an abrasive film, kind of like sandpaper, but much smaller, or sometimes you'll use a slurry solution. Now, these slurry solutions are caustic, the so-called chemical mechanical polishing, or CMP solutions, such as colloidal silica is a common one. And the issue is if you use something like aluminum, maybe, or just plain steel that doesn't have good corrosion resistance, it actually can erode this part rather quickly and damage it. So ideally, we would want to use something that's chemically resistant in the general case. And this led us to a conversation about what are the different stainless steel alloys out there. Because this part is stainless steel, which, if correctly selected, can be corrosion resistant. And so we started having to look at different alloys out there. And do you remember what we found when we started looking into that?
Yeah, and this is why I love this project, right? It's like I started going down these tangents and learning things, big things like these are, metal alloys, what type of products you would use, right? So this was a great project. Unfortunately, there doesn't seem to be a lot of really good intro resources to this. Like I couldn't find, on a cursory like Google search or YouTube search, anything good that introduced you to the different types of steel or different types of aluminum. What I did actually, what I was able to find was that there's a type of steel called 303 steel, which seems to be the most common type of steel used in America. It's also called 18-8 steel because of the 18% chromium and 8% nickel, or vice versa. I'm not certain. Also, what I found was there's a thing called 304 steel, which seems to be almost similar to 303 steel, but it's just made for machining. So I think either one of those is what you probably would go for if you were to fabricate a part, in the US and you didn't have like special requirements. As far as aluminum goes, I actually was not able to find as much information other than I think 6061 T6 aluminum is a very common grade that's used in machining and building parts. So that's the only thing I could find. But actually, it was a very interesting foray into material selection.
And let me also say hello, everyone in the chat. If you have questions, please ask them as we're going along, and I'll try to watch the chat here. So yeah, I think that's mostly what I had as far as the actual machining process and CAD model selection. Did you have anything to add more on this particular part?
So the one thing actually surprised me also was how cheap the incremental price for additional units was to make. So like I would have thought that every incremental quantity you added to your order, it would actually be, kind of expensive, but it was maybe 10 cents on the dollar. Like, you could get 5 for barely, 50% of the price increase, which totally surprised me. Like I was not expecting that. I was expecting like CNC machining time to be the, biggest factor there, but apparently not.
Yeah, I suspect that there's still a lot of time being invested into, I think they just call these shops still, is part of my guess. And then once they get these quotes finalized, I think there's still a lot of tooling set up where, they have to load the end mills into the machine, get the vise set up. I suspect that at least for low quantities, that's still a pretty significant part of the cost run. And it's not until, gosh, I think you get up to maybe even 100, does it really start becoming negligible. I think as I was going from maybe 20 to 50, I think it was still a pretty significant price decrease as the quantity was going up.
Yeah. Yeah, no, and that's why I think this was like the ideal project, not too complicated. Let me prime the whole process pipeline. So I, was able to like take in dimensions, model the part, actually send it to you, get quotes. You had a 3D printed part, which so, we almost closed the loop on it. But I am looking forward to, checking out the metal CNC part, which hopefully we'll cover in, another chat in the future once we get the part in maybe like what, 3 weeks, I guess.
Yeah, I'm still waiting to hear back on some quotes, but yeah, hopefully we'll close the loop on that. We'll get some of that. Maybe this is a good point for me to transition to talk a little bit more about the application and what I want to use this for.
Yes, I think, it's quite a fascinating piece of machinery you use, and, like why, as you said, like why these parts wear out and how they use and, the tolerances involved. I think that'd be a good transition.
Sure, yeah. So at a very high level, what the idea is I need to polish these computer chips to take off different layers. And I've had a few different machines in the past and techniques to do this. You can use acid, for example, to remove the layers. But another alternative is instead of using chemicals, you just kind of mechanically sand away chip layers. They're just kind of stacked on top of each other. And if I want to look into the lower layers of a chip, I can just remove an upper layer. And now I can get better visibility into a lower layer. And this helps me better understand what a chip is doing. And in order to do that, though, these layers are very, very thin, say 1 micrometer thick. And you're talking about sometimes a very large area, maybe, 10 millimeters across. So that means you need an aspect ratio on the order of 10,000 to 1, maybe to get good results. And practically speaking, you need to be less than a layer's thickness to actually have a reasonable consistency. So you might be talking about an aspect ratio of 100,000 to 1 to get a decent result in something like that. And what that means is you need to, across this chip, you need to very, very precisely remove material evenly across a very large area. And if you were just to try to take some hand and sandpaper to do this, you run into a lot of problems, like edges get rounded and other sort of defects where one area gets removed quicker than the other. And so something like a lapping machine is a very precise piece of equipment that helps you figure out how to remove all that material evenly. And in order, even if you have such a machine, it has to be calibrated in a very precise way to make that process work. So the first step I'm doing right now with this new polishing machine is trying to figure out how do I get that calibration to work. And part of that involves taking something like this, which is a feeler gauge, which can read down to say, what is this one scaled for? This one is scaled for mils. That is 1,000th of an inch, as in 25 micrometers. And that allows me to figure out how flat a surface is. And if you look in the setup guide for this machine, they say that for you to get reasonable precision, a lot of surfaces have to be within 5 mil tolerances, I believe is what they call out. I'd have to double check that. I'm sorry, maybe it was 5 micrometers, 5 micrometer tolerances. So actually more precise than this gauge can do, but just as a reference. And that's actually quite small. But the idea then is if I take this gauge and if I can actually mount it to this fixed sample holder right here, I can then load the sample holder in the machine and run this sort of as if it was a sample and see what the run out is on the machine. So in the most basic test, for example, what I would do is mount this in here, and then I would turn on a lapping wheel which spins below. And then as that wheel spins, I have this little feeler here, which I can move around, and the wheel is going to kind of bounce this up and down. And then based on how much that has bounced up and down, I know if the machine is in good tolerance. Does that kind of make sense?
Yes, and in your machine, the sample holder that you showed is stationary, right? It's the wheel below that spins.
In the very basic test, yes. So I would first start by calibrating that wheel there. If that looked good though, then I would actually start rotating this whole thing in circles, because not only could the wheel be out of spec, this bit can also be out of spec. And then once I see how it responds to this rotations, instead of making adjustments to the wheel below, I might make adjustments to this or the machinery above it.
How long does this whole calibration process take, and how often do you need to do this?
Well, the most important thing is if you've just set up a new machine or changed some very critical parts, you have to go through a much more severe calibration like I'm doing now. I've never done this on this particular machine. I'm expecting this whole process to maybe take at least one full workday to complete, just due to the high precision of the adjustments here. If it was a machine that you had calibrated before, I suspect you could go through that process in probably an hour or two would be my guess. Hopefully less if it's already pretty true. Does that kind of answer that?
Yeah, it does. Thanks.
Nice.
How and how long does it take to actually, I guess, slice through the layers on one of these machines? Like, how long would you put a single chip on there for like taking off a single layer?
Well, you use a lot of different grades of lapping films with different removal rates, but the basic idea is that you might put each grade on for maybe 10 to 20 minutes and then repeat that as you've got a few different grades you want to work through. So I would say less than an hour, I would say, for a typical sample, depending on how aggressive you want it to be with removal.
And how do you verify you have taken off enough material? Because like, do you have to dismount the part, put on a scope, check it out, or is there some quicker way of doing this?
Yeah, so there's a few different techniques you can use. The way that I'm going to do it is I would actually fully dismount this from the scope. And you see it has this, part of the reason why it has all these dovetails and these fairly precise surfaces here is so that I can remove this from that equipment, inspect the other side to see how the specimen was polished, and then remount it on the equipment. So in that case, what I would do is I would put this under a microscope and actually just verify on the chip itself. Another way that you can do it, though, is you can use equipment like a monochromometer, which I'm not that familiar with, but I believe those allow you to get very precise measurements on the surface roughness. Using something called optical flats, if you're familiar with those, which allow you to basically get thin film interference, which indicates how precise the surface is.
All right, cool. Very interesting.
Yeah. It's also worth mentioning that as part of this calibration process, I will also a lot of times put Sharpie on here as kind of an indicator. And the idea is that if you put a layer of Sharpie on there, it's very, very thin. And if you look to see how quickly the Sharpie gets removed, you can get an idea of how even it is. Because the layer is so thin, if you see one area get removed before another, you know it's not removing material evenly.
Yeah, I think that people have done videos on how thick a Sharpie mark is. Do you know how thick a Sharpie mark is?
No, I don't actually, off the top of my head. Do you know?
No, but I've seen people take a measurement, and if you think about it, it's just a little bit of ink. No one ever thinks about there's a thickness to it, but in precision work, there definitely is a thickness to it.
Oh, sure. And I guess from my perspective, it would be nice to know it's just the consistency is the most important thing. You just need to be really consistent.
Okay, very cool.
Cool.
And so John, how often have you forgotten about a sample and just worn it away?
Yeah, I have done that before. So fortunately, I haven't done that yet on anything that's really critical. But yeah, I think when I was doing the Sound Blaster project, I did in fact come back and I went to go check on it, and I just looked and there was just a mirrored finish, and I was just like, there used to be a microchip there. So if you're good at those, so yeah, a few things on that note. There's actually a set point on some of the gauges, which you can actually kind of have it as a stop point. And on this newer machine, there's actually a timer. So if I start actually dialing in the process a little bit better, I can actually say stop after 15 minutes. So at least on this machine, I can set an upper bound on how much material was removed. But yeah, on the older machine, you had to manually flick off. And if you got a phone call or had something on the stove, it was very easy to destroy something.
Cool. Well, do you have anything else to show us regarding this project?
Well, I was thinking that maybe as a follow-up to last week, I could do a few quick follow-ups on the bonding removal that we talked about before.
Sure, yeah.
So last week we talked about how to remove bond wires from chips. And I talked about using these liquid amalgam solutions, so hot metal that could dissolve things like gold. And one of the suggestions from our viewers was to try another solution, which was sodium iodide with iodine solution. And this is apparently somewhat corrosive to gold. And I heard that it was relatively selective. That is, it might etch the gold without etching the aluminum. And I gave this a try, and early results were promising. But as I tried it on a few more chips, it actually started destroying the chips. That is, it wasn't as selective as we hoped. And the current theory is that maybe on some of the newer chips, they had different metal layers that would protect the chips, but the older chips that were just pure aluminum, it would just chew through the aluminum. So interesting, but probably won't go into production.
Okay. But that's pretty good, right? Like we got a comment from a listener and tried it out. Good information for you, good information for them.
Yeah.
So in that vein, I actually do have a question for our listeners this week. As I mentioned, I used Fusion360 to create this model, and really nice app, like super heavyweight, super detailed, really industrial strength, but very easy to use, very accessible. Like I would say, anybody, if they, without ever seeing this app, could watch a 20-minute video and actually jump into it. Like it's really well built. The one question I do have is, which I could not figure out, and I tried searching for YouTube videos and stuff, and it didn't seem to be covered, is the versioning and saving of files. So what I can tell is you don't ever save a file. Whenever you click the save button, it creates a new version. So like there's a V1, V2, V3 rev, and you can't really name them. They're just like automatically named V1, V2, V3. You can put a little comment and give a description, but like this particular part, right? I was, this is the first rev. I consider the first rev. This is, V1 I put on the document, and but the file itself had like V6, right? Is this true? Like, do people not save things today? Because I come from a time where control save was like every alternate keystroke because you'd lose all your work. Like, is this a thing that people don't do today, right? So if somebody does know Fusion 360, please go ahead, leave us a comment, send us a note. I definitely love to know like how you handle versioning and in your workflow. Like that'd be pretty good.
Well, I think that's really interesting. I would love some feedback on that myself, especially as I start using that tool more. I think that's maybe a good stopping point for today, unless you had something else to add.
No, I think this was good. And, I have a couple of topics, teaser topics for next week, which I think will be super interesting.
Sure.
Slight follow-up on this week, but quite a whole new thing. So, look forward to that, people. Thanks a lot for watching. This is Geek Monitor.
All right. Until next time. Bye.